So I would like to welcome the second speaker for our session, Depei Qian, who will give us an overview of China's effort on exascale computing, current status, and perspectives. Depei is professor at Sun Yat-sen University and Beihang University, and he's dean of the School of Data and Computer Science at Sun Yat-sen University. He has been working on computer architecture and computer networks for many years. His current research interests include high-performance computer architecture and implementation technologies, distributed computing, network management, and network performance measurement. He has published over 300 papers in journals and conferences. Since 1996, he has been the member of the expert group and expert committee of the National High-Tech Research and Development Program, the so-called 863 program in information technology. He was the chief scientist of 3 863 key projects on high-performance computing from 2002 through 2007. Currently, he is the chief scientist of a national key R&D project on high-performance computing in China. Let's welcome Depei Qian. Thank
you. Okay. Good morning, everyone. It's my great pleasure to be here to share some information in China on exascale computing. So I will give a very brief review in the history of the HPC development in China and the current status of the key project on HPC and some perspectives. So HPC has been identified as one of the priority areas in China since early of 1990s. So in the past 16 years or so, we have implemented 3 key projects on high-performance computing. So here I list the name of those 3 projects. So it was quite unusual to continually support key projects in one area under the National High-Tech Program. So that's reflect the importance of the high-performance computing in China. And the result of the last key project is some petascale, 100 petascale machines. Here I list 2 of them. I don't need to explain that in detail. So one is Tianhe 2 installed in the National Supercomputing Center in Guangzhou. Another is a Sunway Taihu Light installed in National Supercomputing Center in Wuxi. So they are a productive system now, and a lot of applications are running on those systems. So those 2 systems have been listed at the first position on the list of top 500. So this is China's supercomputing infrastructure. So we call the China National Grid. So currently we have about 200 petaflops shared computing power, and the shared storage is about 160 petabytes. And also we installed about more than 400 software and services in the environment. The current user number is about 19,000. Most of them are in group, not individuals. So we have 2 main sites and also 6 national supercomputing centers, 10 ordinary sites, and another 1 operation center. So we have also supported a number of HPC applications, so including the aircraft design, high-speed train design, the oil and gas exploration, and also the new drug discovery, etc. So million core parallelism has been reached by some of the applications. So as we know that 2 of the software has got the Golden Mail Prize in 2016 and 2017. So that's a very brief review of the history. So the current key project on HPC is called the High-Performance Computing Key Project under the National Key R&D Program. So we, in China, we are undergoing a reform of the national research system. So the former high-tech program, key basic program, has been merged into a key R&D program. So the project will last for 5 years, started in 2016 and until the end of 2020. So the motivation of this project to address the grand challenging problems the country is facing by means of the exascale computing power, and to support industry transformation by supporting some important products in China, for example, high-speed train, the commercial software, aircraft, automobile, etc. And also to use the computing capability to facilitate or to help the ordinary people, for example, to develop new drugs and to discover scientific, facilitate scientific discovery, and also some entertainment, for example, the digital media. And to enable scientific discovery, including the high energy physics, computational chemistry, etc. So another important goal is to promote the computer industry by technology transfer. So the major tasks of the current key project include three tasks. The first one is to R&D and novel architecture and key technologies and to develop the exascale computers. The second is to develop HPC application software and also to establish HPC ecosystem in China. And the third one is called HPC environment development. We have to upgrade our current national HPC infrastructure so into a service-oriented environment. So here I listed the projects so far have been deployed by this key project. So each task will be categorized into three parts: basic research, key technology development, and then the demo applications. The first one, only two parts. In the basic research is high-performance interconnect and also the computing, programming, and execution models. For the key technology, that's a prototype for the exascale, and then the exascale computer finally. For the application, there are three sectors. So for the basic research, that's modeling and algorithm, then the parallel algorithm libraries, that's the basic research. For the key technology, including the parallel programming framework and the collaborative application development environment. And for the demo applications, we supported several numerical devices, which is a larger software for simulation, and then domain application software. We have supported around 15 software in different application domains. And the third task, HPC environment. For the basic research, we are focused on the computing service model and the mechanism, and also the virtual data space, which are key issues to be addressed. And for the technology, we are building up operation platform for national HPC environment. And for the demo applications, we are establishing some service system based on the HPC environment. So the first task, the exascale computer development. So the goal of that task is to develop the exascale computer with self-controllable technology. So that's a kind of lesson we learned in the past year's experience. So we just cannot totally rely on the external technology to build our own system. So the matrix for the system is one exascale exaflops peak performance, which is relatively modest compared with US exascale computers. And the memory space is about 10 petabytes. The storage enabling exascale exabyte storage, but because of the limitation of the funding, so we will not implement the real physical storage with exabyte capacity. And the system energy efficiency, this is one important metric. So we have to reach energy efficiency of 30 gigaflops per watt. So also the interconnect, that's 500 gigabps, etc. So those systems developed by the key project will be installed in National Supercomputing Center to support different applications. So there are a lot of technical challenges. As we all know that the major challenges include the power consumptions, the application performance, the programmability, and also the resilience. So for the energy efficiency, that's the most difficult part of the project. So without that limitation, I think it's relatively easier to develop exascale system. So how can we balance the power consumption, performance, and the programmability in one system, and how to support a wide range of applications with still keeping very relatively higher application efficiency, and how to improve the resilience of the system to achieve long-term non-stop applications. So we, before developing the full-scale exascale computer, we have supported 3 prototypes. The purpose of developing prototypes is to test some possible technical approaches for the future exascale. So we will study the architecture, the key implementation technology, the system software, and also verify the system by means of some typical applications. So 3 prototypes are Sugon, Tianhe, and Sunway. So we hope that they will deliver some different approaches towards the future exascale. So some research issues have been addressed by those prototype research. So here I list some research issues. First, architecture. So we have to answer several questions. Should we use special purpose or general purpose architecture for the exascale? For this, because of the number of exascale computing applications is small, should we use a very efficient special purpose architecture to support those applications? But on the other hand, Chinese machine will be installed at the general purpose computing centers. So it's impossible to support only small group of applications with exascale performance. So our solution is a general purpose plus special purpose might be the solution. And the second question is, should we follow the heterogeneous accelerated architecture or the many-core based architecture? So the heterogeneous architecture may achieve better energy efficiency, but the programming is an issue. So better programmability can be achieved by the many-core based system, but because of the limited memory space in the many-core based system, the tuning of the performance is still very hard. And the third question is, should we follow the control flow or adopt some kind of data flow approaches? This is an issue of how to handle the larger scale parallelism. So we can emphasize the larger scale parallelism from the control flow or from the data flow point of view. So our result is that we have to follow application-aware architecture. That means we need to understand the behavior of different architecture in supporting different applications. And the general purpose system will be enhanced by highly efficient special purpose unit. So the philosophy is to follow up kind of a high efficient toolset concept instead of using a universal Switzerland knife concept. So that's a kind of idea borrowed from Professor Andrew Qian from his previous work. A second issue is the processor. So because we are developing different approaches in system design, the requirement to processor is very crucial. So for the general purpose, it's mainly increase the core number of cores, but reduce the complexity of the cores, and also try to widen the SIMD unit. And for the accelerator, we have to identify which part of the application should be speed up. So for the memory, so we are pursuing low ratio of we have to deal with a low ratio of memory to computing power. So probably the hybrid memory architecture will be followed. That means DRAM plus NVM. So NVM has the density, high density, and the low power consumption, but there are also a slow writing and limited lifetime. So we have to tackle those kind of challenges. And also, we have to put the memory closer to the processor, probably use an on-chip DRAM or 3D memory. So interconnect to follow the low power design. So energy consumed by the interconnect is no longer negligible in exascale system. So optical connection might be a solution. So we are trying to make the optical connection closer to the chip. So by means of a miniature of the optical devices. And also the scalability of the interconnect is an issue. And the resilience, the mean time between failure of the future system will be very low. So we have to use hardware approaches to increase the reliability of the system, and also the software approaches to increase the resilience. For example, the traditional the checkpointing approaches might be enhanced by usage of the NVM for fast context switching. And also tools often create a free performance, so it can obtain free performance even greater than using the more expensive hardware improvement. But we need 3 kinds of tools for performance, for the correctness, and also for energy efficiency. And we need the cooperation from processor design, because the processor have to leave room for the counters for the purpose of various performance tools. Now I'd like to see some result of the prototype research. So first, the prototype Sugon adopt a very relatively traditional accelerated architecture using the X80 processor and accelerator. So the purpose is to provide a legacy software asset. So the tested system includes 512 nodes. So the peak performance is only 3.18 petaflops. The link pack performance is about 2.27 petaflops. The efficiency is about 71.5%. So that's a node contains 2 CPU plus 2 DCU. That's an accelerator. The memory capacity is 128 gigabytes of DDR4, and with the interconnect bandwidth of 200 gigabps. So they use a 6D torus interconnect to connect those the nodes. So in the first level, it's a full connection. Then the second level, 3D torus forming a silicon node. Then using another 3D torus to connect the silicon node to form the system. Sugon has developed quite advanced cooling system to lower the energy consumption. So they use low temperature evaporating coolant, so that the system has no need for fans, and the PUE is below 1.1, and also the system will be cooler and increase the reliability and also the performance. That's the first one. The second one is the Tianhe prototype. So Tianhe prototype adopt a flexible architecture to meet the requirement of different applications. So it's based on the new many-core processors with balanced computing and memory access capability. So the system contains also 512 nodes. The peak performance is 3.14 petaflops. The link pack efficiency is higher, it's 78.5%. It has been installed in National Supercomputing Center in Tianjin. So that's a processor. It's an optimized version of the current MT2000 processors with some optimization in energy efficiency and the pipeline structure. So the process contains 128 cores. The peak performance is 2 teraflops, and the energy efficiency is about 15 gigaflops per watt. So each computing node contains 3 MT2000 plus. What? Just cannot. Oh. So Tianhe prototype use interconnect of a 3D butterfly network. The advantage of that network is high performance. So maximum hops is 4 for the whole system. And also, it's fault tolerant, so that means software can control the traffic and also to control the fault tolerance scope. And it has a pretty good scalability to enable connection of more than 100,000 nodes. So they use a self-developed chip to implement the interconnect. And currently, they are working on the next generation interconnect to achieve more than 400 gigabps bandwidth. So the third prototype is Sunway prototype. It's a many-core-based system. So the current system is still implemented using the old processor. That's a Sunway 26010. So the number of nodes is 512, the same, and the peak performance about the same, 3 petaflops. But the efficiency of this system is higher. It's about 81%. So it has been installed in National Supercomputing Center in Jinan. So that's the hardware of the Sunway system. So you can, from the processor, form a node with 2 processors, then form the super node, then connect it, form the whole system. And also, a very efficient water cooling unit is used to cool down the system, and the efficient DC power supply adopted by the system. So that's node. There are 4-way DDR memory, 2 processors. The node energy efficiency is about 11 gigaflops per watt because its old processor is used now and will be improved in the future. So that's a software stack of the Sunway prototype, including a complete software stack for the homegrown processors, including the multi-domain OS, the Perl language and the compilers, the high-performance storage management system, and also the parallel program development environment. So that's the prototype. The second task of our project is application development. So we have some basic research on modeling and algorithm. We selected some application area and abstract the common mathematical problem like large-scale linear and nonlinear equation, the matrix eigenvalue problem, etc. And then we do adopt some application-driven approaches to invent novel, scalable basic algorithms towards those problems. So here is some example of the algorithm used for blood flow dynamic simulation and seismic analysis of the Guangzhou Tower. Those have been deployed on Tianhe 2, reached more than 10,000 scale of parallelism. And also the second category application is numerical devices. By means of numerical devices, we refer to a complete set of software to help the simulation of a specific domain. So currently we have supported 4, the numerical aircraft, numerical reactor, numerical earth system, and the numerical engine. Use the numerical aircraft as an example. So we will implement a function for aerodynamics analysis, aeroelastic analysis, structural analysis. And with that 3 functions, we can implement multidisciplinary optimization to covering the aerodynamics, structural strength, and the fluid solid interaction. That's the second numerical devices called the numerical earth system. So we develop models for studying climate change and also develop a nonlinear coupling method for multiple physical and chemical processes covering the atmosphere, ocean, land, and sea ice, etc. Oh, that's parallel software for the design of fluid machinery. So 4-stage turbo, full circle, unsteady parallel simulation has been conducted with that software. So it achieves a pretty good parallel efficiency and speed up. And this is software for modeling complex engineering project. So the 3 gauge full dam was used as an example of modeling. So the dam length is about more than 2,300 meters. The height is 180 meters. So the simulation covers the full process, including construction, nonlinear material, creep deformation, nonlinear contact, etc., and also the thermal mechanical coupling. So that simulation has been implemented on Tianhe 2, reach a degree of freedom of 80 million, and we're using more than 3,000 cores and to solve the linear equation of order of 558. So new drug discovery. So we have developed free energy perturbation approaches for discovery of new highly potent inhibitors towards a drug target. So this software is more accurate than the current advanced drug design software. So with this software, we improve the PDE-10 anti-tumor activity, increase that by 2,000 times in 2 months. With a traditional method, that takes about 3 years. So that's the, also we use that software to do the virtual screening for more than 42 million compounds in 1 day. It will take about 3 years on an ordinary computer. So that's the only non-simulation parallel software they call it RenderWind. It's a parallel photorealistic rendering software. So that software was deployed on Tianhe Light using 1.3 million cores. So the software covers 3 parts: the parallel photorealistic render engine, the distributed light tracing engine, and also the light tracing cores, which is installed on the core of many core processor. So this software can implement larger scale parallel light tracing the rendering problems to handle the larger scale scene processing. And to enable efficient application development, we have also conducted some enabling technology research. We continued our work on the parallel framework, parallel programming framework work. So we focused on 5 parts of the framework to support structured mesh, unstructured mesh, mesh-free combinatorial geometry, finite element, and also one new element that's a graph computing to reflect the support to the big data and AI. And the philosophy is to use that framework to ease the programming. So we can serial programming and debugging on PC and to translate into efficient parallel execution on supercomputers. And another new work is application development platform. That's an effort to establish the application ecosystem. So we will establish domain-specific programming environment, support rapid application development, and provide the tools for performance, the efficiency, and also the pre- and post-processing, and to build up also the application software repository by integrating and reuse of application software. That's the second part. The third part is the environment. So we have upgraded the China national grid into a service environment, increased the number of operation centers. Currently, it's a 2-center environment, 2 operation center operation. And also, we changed the software for the access the environment. The new portal with a micro service structure has been developed. And also, we somehow continually our development in the monitoring and the management of the system. Here is the interface of monitoring of the CNGrid. So that monitor can monitor the status and the usage of different resources in different centers. And also, we developed an industrial application village over CNGrid to support industrial applications. We propose a wholesale-based resource provisioning and retail-based on-demand user service model to facilitate usage of this village. And also, one new platform has been developed called HPC Education Practice Platform. So on top of CNGrid, we build up a service platform so that the HPC education practice can be supported. And also the content of the education is also developed and installed on that platform. So this is one part of our effort to improve our talent on HPC. So that's the current status of the key project. Then I will say a few words about the perspectives. So we will put more attention to the bottleneck technology, which will limit the advance of the high-performance computing in China. So we have learned that lesson in recent years. So that means we have to find out where is the bottleneck and how to handle those bottleneck issues. So we have identified several important bottlenecks. For example, the processor, including the mechanical processor and the accelerator, the interconnect, especially the optoelectronic devices to implement the network, and also the 3D packaging technology. For the memory, the 3D memory is a big issue. We don't have that capability in China now. And the storage, mainly the SSD-based storage and also new storage devices. And the software is a big issue, especially for the engineering computing software. It takes probably will take longer time to improve. So that's another important bottleneck. And the second thing is to build up the application ecosystem. So because the future exascale system will be implemented with our homegrown processor. So the ecosystem become very crucial issues. So we need the language, compiler, OS, runtime to support the new processor. And also we need some binary dynamic translation to execute commercial software on our new system. And we need the tools to improve the performance and energy efficiency. And we also need application development support. And so this is a very long-term job, need cooperation between industry, academia, and also the end users. And third issue is how to support the emerging applications. So we will emphasize the support to the emerging HPC applications, especially the big data and the AI, by means of exascale computing facilities. To support the big data applications, that means we will need new mathematical methods and computing algorithm. And also we need different software stacks to enable the applications. And we need architecture support for the big data application. For example, the data intensive versus computing intensive, the latency or bandwidth sensitive. So those are possible architecture support for the big data applications. And how to support the AI applications, very straightforward to use HPC to enable the very high performance training. And the mixed precision of floating point operation might be considered by the future processors. And also the efficient AI algorithm and the frameworks will be developed, and architecture support also for the micro architecture level and also the special purpose accelerator. And we will emphasize the converged development of HPC, big data, and AI. So HPC, big data, and AI, in fact, are really tightly related to each other. HPC is the basis for big data processing and also the AI applications. But big data also change the way of AI applications. So, but on the other hand, which has been less emphasized, is the influence from AI and big data to computer architecture. So the future supercomputer will be deeply influenced by the big data and the AI applications. So data-centric or data flow architecture probably will be restarted. The neuromorphic computing approaches and also intelligent accelerators, those will be consideration in the future supercomputers. And we hope that those three sectors will be developed convergently. By convergent development, we mean that each party will be indispensable. And having three will be much better than having only one. And also, we identify some example of the converged development. For example, AI and the big data enable scientific discovery, and also smart medical and healthcare systems. So finally, we have to follow or pursue sustainable development of HPC environment. This is a very unique issue in China. So because we don't have stable, reliable operation funding from the government for our environment. So we have to propose new operation mode and the technical approaches to support the new mode for the national supercomputing infrastructure. Try to solve the issues of the funding issues. For technical issues, including the resource grading and admittance and the quality of service, the billing policies, the mixed mode operations, and security, and also the integrated management. And we need technology to better support the application village development. That means the on-demand resource provisioning and the usage, and also the agile construction of the new application village. That's a kind of consideration in the sustainable development of the HPC infrastructure. So I would like to stop here and leave some time for questions.
Thank you for an excellent presentation, and we have a few minutes time for questions. So please again step up to the microphones in the aisles and state your name and your question.
Hi, sure, I'll go first. Tiffany Trader with HPC Wire. Thank you, that was such a broad and comprehensive overview. Thank you for that. So I'm going to step a little bit away from that and go a little bit more generally. I'm wondering what your thoughts and perspective are on Moore's Law and planning for post-Moore's Law in China, and we're seeing increasingly the signs of the limits there, with some delays in the next process nodes and global foundries dropping 7 nanometers. So, what's China doing to ensure that there's a sustainable path for the future of microprocessors?
Yeah, microprocessor is a major issues in developing exascale. So currently, from the prototype, we still use the current version or slightly modified version. So for the next generation, the work is still on. So I don't know if we will follow the Moore's Law, or anyway, we are trying to solve the technical issues in developing the new processor.
Are there any specific emerging technologies you can point to? I mean, there's a lot of work. DARPA's doing work funding chiplet innovation, 3D packaging, innovative packaging techniques.
So far, I don't have much to say for the emerging technology. So because we are relatively weak in this aspect, we can use technology, the external technology. We are also developing our own technology. I think on the architecture design point of view, from that point of view, we are relatively in a good shape. So our team is pretty good in design and also in the optimization. But on the other hand, in implementation, especially in the foundry part, we are still struggling. I think we have to adopt the newest technology. That's a difficult part of our work, I think.
Okay, thank you. Any other questions? I don't see any others, so thank you again for a broad and informative presentation.
Thank you.
And good luck. Thank you.